All right, what's going on, everybody? Professor Bryant with another of mini lecture series. I was asked to do a video on valence bond theory, specifically hybridization, and its three-dimensional structure. So I'm going to try to show some written diagrams on paper as well as show some three-dimensional models, and hopefully that will help with everyone's understanding. So first, we're going to attack Sp3 hybridization. Hopefully we remember and realize that when we're dealing with Sp3 hybridization, what we have done is we have hybridized three of the p orbitals, right? The px, py, pz, along with one of the s orbitals to create four new hybridized orbitals that are in the shape of a tetrahedron, right? The tetrahedral geometry that we should be familiar with at this point. Okay, the first molecule of interest is we're looking at hydrogen chloride, and if we make the assumption that the chlorine atom has undergone hybridization to create this single bond, this sigma bond, right, an overlap of these orbitals head to head, then we should expect to see it have a tetrahedral geometry. What I have shown here is the center of these hybridized orbitals is where the chlorine atom is itself. The lone pairs reside in these three lobes of the hybridized orbital, and then the covalent bond that is shown here is going to be found in that one lobe overlapping with the s orbital of hydrogen. This is linear, right? Remember, molecular geometry has to be linear for an atom that molecule that only has two atoms. Now, what does that look like in a model? So here we have a model. What I'm showing you with the brown spheres are lone pair electrons represented on the green chlorine atom. We have tetrahedral geometry on the chlorine atom, and we see the sp3 lobe extending from that chlorine and bonding with the hydrogen, which is shown as the white sphere. So this is what in three dimensions the hybrid orbital would look like, and then we have lone pair electrons that reside around the chlorine. This is a sigma bond, and otherwise you would need to know that we have a polar molecule, right? Net dipole towards chlorine, bond dipole in that same direction. Okay, now let's take a look at another sp3 hybridized molecule. Is we have chloroform, or CH3Cl, and this, or chloromethane more specifically, excuse me. And chloromethane is carbon at the central atom and a tetrahedral arrangement in the Lewis structure. We show one going into the paper, right, one coming out of the paper, and then two bonds in the plane of the paper. This is tetrahedral molecular geometry. It is also sp3, so we should expect it to have 109.5 bond angles, and I have shown that drawn here in three dimensions, where the chlorine is going into the paper, and then the three hydrogens, two of which are in the plane of the paper and one is coming out. Where you see me darken the lobe, we are talking about a situation where it is coming out of the paper. Let me zoom in just a little bit more. Maybe we can get a closer look. Okay. So from here, the model I have arranged is here, where we have the carbon in the central atom, which is blue. We have four sp3 orbitals extending out from the carbon atom that we're focused on. We have three of those bonds to the hydrogens, as you can see in these three. And then we have the chlorine atom in green still, with the three lone pairs about the chlorine atom. I just showed these to you just to kind of give you some representation, right? Remember, chlorine has got three lone pairs in the Lewis structure. So we have a three-dimensional structure. We have these sigma bonds everywhere, right? We have the sp3 orbitals overlapping with the hydrogen atom s orbital. So here is the structure for chloromethane. All sigma bonds as well, and we have a bond angle, remember, of 109.5 degrees, right? If we want to talk about polarity, we have bond polarity that exists in the direction of chlorine, and we also have overall molecule polarity in that same direction. Okay. Phosphorus trihydride is also sp3, but in this case we have only 3 bonding domains and 1 lone pair. Our molecular geometry is trigonal pyramidal, and if we see our drawing, we have 1 lobe of our sp3 hybridization containing a lone pair, and the other 3 containing a sigma bond to each of these 3 hydrogens. Now what does that look like in the model? So in the model, that looks like such. Looking from the top down, we see the lone pair. If we look from the side, we see trigonal pyramidal geometry, and we see sp3 lobes, again still bonded to the hydrogen atoms, right? To the hydrogen atoms. Now, when we talk about bond angle, remember, because of a lone pair, we expect this bond angle to be less than 109.5 degrees. We also expect polarity to exist and a bond polarity to be up towards the phosphorus atom. Again, the model here, tetrahedral geometry on the electron domains, but trigonal pyramidal geometry because we have 1 lone pair. Again, lone pair represented by the brown sphere. Okay, the last of the sp3 orientations is we're going to use water, right? Water, very familiar Lewis structure. Here I've drawn the 2 lone pairs in the plane of the paper, and then I've drawn the 2 singly bonded hydrogens, one coming in and one going out of the paper. Again, these are sigma bonds. We have sp3 hybridization. So drawing this appropriately, we have 2 lobes that have a lone pair in each of those, and then the lobe coming out of the paper and into the paper, both singly bonded to the hydrogen, and we see that these are sigma bonds. From a model perspective, we see 2 lone pairs, tetrahedral electron geometry, where the 2 sp3 lobes that are used in bonding are bonded to these hydrogen atoms. So here's the model for water. Again, when we talk about water and having 2 lone pairs, we should expect that the bond angle here is also less than 109.5, right? So just looking at any of these examples, you need to be able to draw the Lewis structure and then tell me the hybridization as well as draw the hybridization in the 3 dimensionals and explain which kind of bonds are occurring. Okay, let's take a look now at sp2 hybridization. So when we're talking sp2 hybridization, first thing, the example that was used in class is BH3 boron tetrahydride. Remember that boron is the octet exception, and we're using this to explain a concept, but boron does not need 8 electrons, so it is the octet exception. So with that being said, the Lewis structure, the correct Lewis structure is drawn as such, and the 3-dimensional Lewis structure is also drawn as such. Because it has 3 bonding domains around a central atom only, we get a molecular geometry of trigonal planar, and that gives us a hybridization of sp2. We have taken 2 of the p orbitals and 1 of the s orbitals to make 3 sp2 orbitals, which are here, and this is the sp2 representation, also drawn in 3 dimensions because it is flat. They are all in the same plane. Now, when we look at it from the side, however, we see that there are the pz orbitals that are left over, and those orbitals cannot be disregarded because those orbitals can be used for bonding if necessary. So take a look at that model. What we have is, you can see that I have now utilized these lobes, or these p orbital shapes, that are representing the unused p orbital, right? That's what we have here. So if we take a look at this, we see that we're dealing with planar geometry, trigonal planar geometry for the sp2 hybridization orbitals, but we are still with pz orbitals that are shown here in the z-axis, right? So this would be the side view that you see here, and then the top view would look a little bit something like that. Okay. All right, and again, from an angular perspective, bond angle here 120 degrees. Have to know that. Again, another look from the top, trigonal planar, and then from the side with the p orbitals in the z-axis. Now, as far as polarity is concerned, again, magnitude of the vectors would all be the same, so we would have a nonpolar molecule. If there were 3 bond dipoles, they would cancel one another out. All right, and lastly is SP hybridization, and we also have an example from the text that we saw in class that is also an octet exception, and that would be beryllium dihydride, or BeH2. If we look at this in Lewis structure, we see the Lewis structure is 2 single bonds, and again, back up here, these are sigma bonds, right? If we take a look, let's make sure this is clear. We have an H here, an H here, and an H here, and these are sigma bonds as well. Same thing here. From the side, the H will be there, H will be there, and H will be there. Okay. Now, BeH, we have head-on sigma bonds onto the sp hybridization, right? These are the sp orbitals. And there we have the 2 hydrogens overlapping head-on. Now, remember, because we have only used one s and one p, we have 2 p orbitals that are unhybridized and left over based on this theory, and these 2 I've represented as px, py, and remember, going into the paper is the dotted line, and then the more solid line or the darkened line are coming out of the paper towards you. Now, what does this look like in the model format? If we were looking at it from the side, it would look like such, right? We see that we have linear geometry, but if we were looking at it from the front, we would see this orientation, right? Where we were looking at the p orbitals and looking in the plane of all of the 3 atoms, okay? Where the central atom is the beryllium, so linear, looking at it from the side, and then looking at it from the top, where the different colors here are px and py, px and py. Now, bond angle here for linear, we know is 180 degrees. And again, if you were looking at this from the front, you would see something that looked a little bit more like that, where these is px, py, and px, and then this will be the hydrogen atom. You'll be looking at the front end of it. Okay, so being able to represent these 3-dimensionally is going to be very important. I look forward to a Workout Wednesday video where I do some more drawings, particularly for the molecules that involve double and triple bonding, as well as molecules with multiple central atoms. If you have any questions, you know where to reach me. Feel free to email me, and I will see you guys soon.